Now shall see some definitions. What is a nowhere dense? What is called as a nowhere dense set? That is a definition. The subset A in R is said to be nowhere dense in R if the closure of the set contains no non-empty open interval. That is, a set is said to be nowhere dense if the closure of the given set does not contain any open interval. That's all. This is the definition, and using this we are going to say some of the sets what we studied earlier are nowhere dense sets. Suppose closed sets. Suppose you consider closed sets, say F is nowhere dense. When it is nowhere dense if it contains no open interval in R. Here the definition says that is the closure of A only should not contain open interval, but here why we are telling a closed set? Because if a set is closed, then if a set F is closed, then the set is equals to what? The closure. So instead of dealing with the closure, we can state the definition in terms of the set itself, if it is a closed set. Suppose if F is closed set, the definition is simplified. Instead of A bar, we simply put E. So if a set is closed set, the set is the set is nowhere dense if it does not contain an open interval. That's all. So this is one important thing you have to keep in mind. Next, set of all positive integers. Set of all positive integers is nowhere dense in R. Why it is nowhere dense in R? Since you can see the set of all integers, this is the real line. Set of all integers, only the integers 0, 1, 2 like this, and this side it is -1, minus. Only the dots are in the set. All these things we collected and we call it as set of all integers Z. 0, plus or minus 1, plus or minus 2, plus or minus 3. So now all these are, you can consider them as a single point sets. Already we discussed singleton sets are closed. Singleton sets are closed in any metric space. Singleton sets are closed in any metric space. So all the singleton sets are closed, and if it is a singleton set, definitely can't contain any open interval because it is having only one element. That set cannot contain an open interval, that cannot contain an open interval. And here the thing is, here you cannot you cannot suppose these two elements are there, and overall this integers, set of all integers cannot contain any open interval. Cannot contain any open interval. That's why the set of all integers is nowhere dense in R. And every singleton set is closed, and all the limit points are inside the set itself, a singleton set itself. So set of all integers is closed one, as well as it cannot contain a open interval. It cannot contain, see, an open interval, it is like this. For example, any open interval should be continuous form like this. So but the set of all integers contains only these dots, so it cannot contain a continuous set of numbers. So that's why it cannot contain an an open interval, and each element in the set is a closed set. And this is the result. And the next one is about the Cantor set. What about the Cantor set K? First we will tell that Cantor set is a closed set, because it is the complement why it is closed set, that we are going to explain. Why Cantor set is closed? Since its complement is union of open intervals. As you can recall how the Cantor set is formed. First in the set 0, 1, by 3, 2 by 3, like this. Suppose open middle third we are removing, so this is removed. So open middle third is removed, and like this in each step we are removing an open interval. So whatever we remove is an open interval. Union of all open interval, an open interval is an open set. What we proved it. And union of all open intervals is an open set. So whichever removed, that is the complement of Cantor set. So union of open set is open, therefore union of all open set is open. So the complement of Cantor set is open, therefore Cantor set must be closed. So that's why Cantor set is closed, since its complement is union of open interval, that is open set. And now we are going to say that Cantor set is of is a nowhere dense. Further, Cantor set K is nowhere dense in R. Why it is nowhere dense means it cannot contain an open interval, because all the open intervals is removed. Since all the open intervals are removed to form K. So we are removing open intervals in each step and keep on continuing. So each time we are removing the open intervals. So it cannot contain any open interval. That's why it is nowhere, and already we proved that it is closed set. So a closed set as well as it contains no open intervals. Therefore, as per the definition, we can tell that counter set is a nowhere dense set. So these are the things. And now the next definition we are going to check. What is called as a set is of first category. What is a first category set and second category set in R1? That is the next definition. The subset D of R1 is said to be of the first category if that given set can be written as union of some sets where each en is nowhere dense. It's nowhere dense now. If D is not of, if it is not a first category, we say D is of second category. That's all. That is the meaning of first category. So what are the simple results we have considered? Set of all positive integers is nowhere dense, counter set K is nowhere dense, and it is closed, as well as set of all positive integers is also closed set, because there exist all the limit points of positive integers is inside set of all positive integers. Suppose any limit is there, that is definitely inside R itself. Because all singleton sets, what are the, for example, the set 1. Suppose I take a singleton set 1. What is the only sequence available? You can form a sequence like this. Definitely it converges to 1. This 1 is element of set. So whatever sequence like this we consider, which is having a limit, the limit is inside Z itself. So that's why Z is closed. Okay, like this repeated sequence, this kind of sequence only available in Z. So that's why Z is closed, as well as it is nowhere dense, because it cannot contain an open interval. It cannot definitely contain an open interval. So these are the two important results.